Preparation of aldehydes and ketones from alcohols and alkynes. These two reactions, these two preparations we are going to discuss now. First of all, see how to prepare aldehyde and ketones from the primary and secondary alcohols. If you want to prepare aldehyde and ketone from primary and secondary alcohol, we have to perform oxidation reaction. Here you can see this is primary alcohol. If CH2OH group is present in any alcohol, that alcohol is a primary alcohol. We have to use a reagent, number of reagents available for the oxidation, and then you remember you have to remove hydrogen attached to the oxygen and the hydrogen attached to the carbon where oxygen is attached and put there a double bond. You will get this carbonyl compound. So removal of hydrogen is nothing but the oxidation, and this reaction you are performing by using a reagent. So if primary alcohol you are using for this reaction, you will get aldehyde. And if secondary alcohol is used, secondary alcohol means what? Here alkyl or aryl group and only CHOH group is present. CHOH group means secondary alcohol. Doing the same thing, you have to remove hydrogen from oxygen and hydrogen from carbon where oxygen is attached by using a reagent. So if and putting double bond between carbon and oxygen, you will get this ketone and the hydrogen is removed. So this is again oxidation reaction, but when secondary alcohol is used, you get a ketone, and when primary alcohol is used, we get here aldehyde. So which reagent we are using? We are using PCC. PCC is nothing but the pyridinium chlorochromate, and its structure is given here in this box. Now I'll quote here one example. You first of all watch that which alcohol it is. So CH2OH group means it is primary alcohol, and you know primary alcohol gives aldehyde. So you have to remove hydrogen from the oxygen and the hydrogen from the carbon where oxygen is attached. Here CH2Cl2 is dichloromethane, which is used as a solvent, and when you remove hydrogen from carbon and oxygen, put there a double bond. So you will get here your carbonyl compound, that is aldehyde. So benzyl alcohol is converted to the benzaldehyde by using the pyridinium chlorochromate. Now we are discussing second preparation, that is preparation of aldehyde and ketone from the alkynes. Alkynes means triple bond. So you focus on triple bond, whatever structure is given, and hydration is nothing but the addition of water. So you have to add hydrogen at one carbon and OH at another carbon by using this bond, and you have to join hydrogen by using one pi bond. For this purpose you are using 20% H2SO4 and 1% HgSO4. This reagent you are using. Now I have joined OH here and H here because both carbons are symmetrical. You can join hydrogen either at this carbon or at this carbon and OH on another carbon. So this is nothing but the enol. So this will undergo tautomerization. Tautomerization means what? Where hydrogen is going to change its position. So the bond which is attached to the oxygen and hydrogen, which is attaching hydrogen and oxygen, you have to shift in between carbon and oxygen to form a carbonyl group. Now this hydrogen you have to join to the adjacent carbon by using this pi bond, so you will get this carbonyl compound. So this carbonyl compound is produced. Now here I am taking two examples. One is symmetrical alkyne. How to decide symmetrical alkyne? You cut this molecule into two halves. If this half is similar to this half, this is symmetrical alkyne. In case of symmetrical alkyne, you need not to worry. You can join hydrogen either this carbon or this carbon, and OH anywhere you can join, you will get the same product. I'm using this reagent that we have discussed here. Now joining hydrogen to this carbon by using a pi bond and OH to this carbon by using this sigma bond. So again you can form this enol, and enol undergoes tautomerization to convert that carbonyl group. But I have skipped that part. I have skipped this tautomerization part, and I'm going to tell you one trick. So you have to join in fact two hydrogen at one carbon and oxygen at another carbon by using a double bond. So you can join here two hydrogens here at this carbon, removing two pi bond. One pi bond is used to join this hydrogen and another pi bond is used to join another hydrogen, and these you have to join oxygen on another carbon. So the triple bond is converted to the single bond and you will get your answer directly. So this is the trick. You can skip this enol portion or you can skip this tautomerization part to get your answer. But if alkene is unsymmetrical, how to decide? Just I mentioned here, you cut this molecule into two halves. This half is not identical with the this half, so this is not symmetrical. In that case there is a problem where to attach hydrogen and where to attach OH. So in that case you have to use Marconi-Kopp's rule. I wrote here Marconi-Kopp's rule very shortly, YUM rule, that means Marconi-Kopp's rule. According to that rule, hydrogen will go to that double bonded carbon where more number of hydrogen present. Here if you compare hydrogen, at this carbon there is no hydrogen, but at this carbon there is one hydrogen. Obviously hydrogens will go to that carbon. So as I mentioned here, you have to join two hydrogen to the carbon where more number of hydrogen present. So I joined these two hydrogens here at this carbon because one extra hydrogen is present here, and this triple bond is converted to the single bond and oxygen will go to there to the another carbon, and that you have to join by using a double bond. You will get your answer. So in case of unsymmetrical alkyne, you are using Marconi-Kopp's rule to get your answer. So in this way you can prepare aldehyde and ketones from primary, secondary alcohols and symmetrical, unsymmetrical alkynes. Thank you.